Hello everybody, this is again Dr. Sergey Sarkisov, and today we'll work on polar graphing and understand what polar coordinates are in general. So let's go ahead and take a rectangular coordinate system. Okay, something we can look into as far as the Cartesian coordinate system with the x-axis, the y-axis, right? That's x and that's y. Well, what polar coordinates are is basically, let's say polar coordinate are theta. Okay? You usually begin with a pole, like an origin, right, where the spot where you start our rays are rays from. And so you have a pole and you have a polar axis, and now let's say you're going at some distance. So instead of me saying you know x y, let's say r is 4 and angle theta is, let's do degrees, 30 degrees, okay, instead of radians. So that would mean that you go 30 degrees this way, okay, and you go the length of 4, okay. Let me kind of do that neatly here. At 30 degrees, that would be like this, right? And so there is now this is, if this is 4 and this is 30 degrees, okay, we actually get that point, and that's called the polar coordinate there, plotting it. And this is the polar coordinate for 30 degrees. And actually, if you had a polar coordinate system versus a rectangular coordinate system, it would kind of have a bunch of these circles of radii 1, 2, 3, 4, and so on. Let's see, let me kind of see if I can do that neatly here. Let's see. So that's like, let's say you're trying to make, instead of graphing paper, you want to have like polar coordinate paper, right? So that would be like this, something. Let's see. And that's radius 2, and then let's do like a few more circles just to kind of see what's going on. Let's see, radius 3 circle. Let's see, I'm just trying to construct a little polar graphing for myself. As you can see, let's see, there's that. Radius 3 circle, we're trying to do that, and this. And then this, okay? And then that's 3. That's a 1, 2, 3 units. Let's do one more. Let's do a 4 unit like this. And that should be kind of a 4 unit there. Let's see. So there's that. Let's see, see, I'm just kind of playing around with circles until I can get it, to work out neatly here and nicely. And so there is our radius 4 circle, and you see that point should be 4 away. That's why this is helpful. 4 away from the origin, from the pole, and right there is our point. This point here is the point, and let me actually make it a little neater. So now you can see that that point right there is 4 for the distance away from the pole, okay, and at that angle or direction, or of 30 degrees, right? Actually, this is sometimes called the magnitude or the modulus, okay? This how far away you are, and 30 degrees a lot of times is called the argument, okay? Like what direction you're going, what's the angle. And so it's like a vector in a sense. If you remember vectors, you have the distance and you have the angle, or you have the direction. So you basically know where you're going from and in what direction and where you're going. So this is kind of 2 pieces of information. It's like almost like a vector where you have the scalar and the direction, right? So where you're going. So again, this is 430 because you're 4 away from the origin. You're at 30 degrees, and you can actually convert it to x and y, right? This is the r theta, let's say, is equal to 430, for example. Then xy, you have a point there also with the rectangular coordinate system, right? Which is going to be, you can see this is actually what? Well, it's a 4. It's actually r cosine theta. Remember that's how you do the x value from the r and theta, even when you do the unit circle or whatnot for the trigonometry. And this is going to be r sine theta for the y value, right? Because again, let's just look at it quickly here. Why is that the case? Let me remind you, because sometimes we don't understand. We just copy, the components, r sine theta, r cosine theta. But the reason is, let's say this is x and this is y, right? And this is my r, and here's the theta. Remember, what is the definition of cosine theta? It's adjacent, so x, over the hypotenuse, r. and you solve for it, you get r cosine theta for equals to x, for solve for x. Similarly for y, right? Sine of theta is equal to opposite over hypotenuse, y over r, and so y is equal to r sine theta. That's where we get these, okay? So then we kind of, let me just kind of say this is the work for getting that right there. That information of y, x, y would be also represented by r cosine theta or r sine theta, okay? And you can actually see what is our x, y then. It's equivalent to what's 4 cosine theta. It's actually 2 root 3, right? Check that if you need to. And 4 sine theta is 4 times a half, it's just a 2. And you can see there's a height of 2 there, right? That's a 2, and that's going to be the 2 root 3. Okay? Now, that's just a polar coordinate. Now, how do I graph something kind of fancy like this? Watch. Let's do a few graphs, some cool shapes, some cool graphs that we can do. What can we do with polar coordinates that is more interesting even than if you do rectangular? Well, let's see. Let's first of all graph the graph r equals 3. What is that? Okay, that means that no matter the angle, you can go in any direction. There's no restriction on theta. The radial distance from 0 from the pole is equal to, from the origin is equal to 3. So there's 3 this way, and then you change the angle, you're still going 3. You know what's going to happen? This is easier than even saying x squared plus y squared is equal to 9 or 3 squared. This is just a circle of radius 3, right? So you just go around, around until you get a circle where all the points are radius 3 away, or distance 3 away from the pole, okay? And so that's that. That's what the shape of our graph r equals 3 is. Interesting, right? Let's try another one, another graph. Let's try, let me go ahead and do that again, the rectangular coordinate system, or the x-axis, y-axis. And so let me try this one. What if I said, hey, r is equal to, let's say, pi over 3. Okay, well, let's do pi over 4. Okay, so now what I mean, let me change it a little bit. Let me call it theta. Of course, the angle. That's what I was going for. Is equal to pi over 4. So you're given an angle. You have no restriction on how far away you go, the r, but the angle is pi over 4. So you're always going in this direction, right? Pi over 4, 45 degrees from kind of the starting, the initial side, and going to the terminal side of the angle, right? So there we are, and that's that. But also the r can be negative, and so you can be going backwards, and you're getting a line. This line looks like y equals x, right? The slope 1, and there's no intercept. It's actually the line y equals x. Line. That's how you would graph this. But one more thing you want to notice is the following. So think about it. We said, remember, that x is equal to r cosine theta, y is equal to r sine theta, right? Now, what if I divided the two equations? Let's say y over x. Guess what happens? You get tangent, right? Remember, tangent opposite over adjacent? You do get tangent is equal to y over x. And if you actually do x squared plus y squared, you get what? R squared sine squared plus cosine squared, right? Or cosine squared plus sine squared. And that's equal to r squared. So r is actually equal to what? The square root of. And we don't say negative or positive. We just say square root of positive square root of x squared plus y squared. Why? Because again, the distance itself that we're going into is going to be the positive. Now, if you have an angle, that would give you the what? The actual which direction you go. Now, you could actually have a negative r as well. You can. Okay. There's nothing saying you cannot, because if you do have that, then you're just going backwards. So that's fine too. But we're going to say this positive square root of the square root of x squared plus y squared. Okay. So that's another way to write it. So you see how what happens is we have an angle, theta is equal to pi over 4 there. That's equal to what? Arctangent, actually, of what? Y over x, because y over x, remember, tangent of that, pi over 4. So take tangent of both sides, tangent pi over 4, which is exactly a 1, right? Is equal to y over x. Get rid of the arctangent there. And that's why you get, if you're going from the polar to rectangular, you go y equals x, right? Solve this. You get that, okay? So that's where that y equals x line comes from. And actually this one, that comes from where? Well, r is equal to 3 is equal to the square root of what? X squared plus y squared. And so then you're like, okay, square everything, 9 is equal to x squared plus y squared, and that's exactly the circle centered at 0, 0, with radius square root of 9 is 3. Okay, so circle, center, 0, 0, radius 3, right? That's what it is. R equals 3, so right away we have that. Okay, okay, now let's do some fancier polar coordinate graphing. So let me try another one, really cool one. Let's see. What if we go straight for something kind of more challenging like this? Let's do one like r equals to 5. Let's do 4 sine theta. Okay. What would happen here? Well, what you think is as you're changing angles, the radial distance, the distance from the pole changes, right? The how far are you going to go away from the pole? The polar coordinate, how far away it is from the pole, is going to be changing. So let's see. We're going to think about, okay, if theta is usually start at 0, what's sine of 0? It's 0. So 4 sine 0, right? If you're actually going this direction, 0, you're actually not going anywhere. You're going to be r equals 0, right? So you have, what you can do is you can actually make a little diagram of some values for, here's theta, here's r. I usually do r after theta, even though the polar coordinate is usually represented by r theta, right? But so 0 gives me a 0. What's 4 sine of, let's say, give us some angles like easier ones like 30 degrees or pi over 6, right? Well, what's 4 times that? That's actually 4 times a half is 2. 4 times, let's say, pi over 4 is a 2 root 2. You can check these. 4 times pi over 3 sine of that is going to be 2 root 3, okay? Which is approximately 2.8, right? This is approximately, there's a 1.7-ish, 3.5, right? So double that. And then try pi over 2, and you actually get 4 times sine of just the pi over 2. That's a 1, 4, right? Then, and that's actually the maximum you ever get. So what happens is you have, look, at 30 degrees, you have what? Let's see. You have a 2, right? So let's say this is my 1, my 2, my 3, my 4. Okay, so you're going to get this kind of 2 right there at 30 degrees. Okay, okay, great. What about and by the way, as the angle is as the angle's increasing, as we're going this way, r keeps on increasing, the sine's increasing, right? So you're actually doing this something like that. Okay, and then what happens at pi over 4? We get, let's see right here, we get a 2 point what? About 2.8-ish, right? So that's about right here. Let's see, like that. So here we are, like that. We have a point there, right? And so we're kind of increasing, increasing, increasing. Let's look at pi over 3. All right, we have this, and we have actually almost a, let's right there, 3.5 about. So we have about a point right there, okay? And then finally, what about let's say pi over 2? That's a 4, right? So 1, 2, 3, 4. And so what happens is we have actually kind of almost like a semicircle going on for some reason, right? You get through all these points, kind of like that, right? Okay, interesting. Why is that? And so, by the way, think about this. Now, what if I add a few more angles in there? So continue going. You did the first 90 degrees, 0 to 90, the 0 to pi over 2. Let's go more. Let's go like 2 pi over 3, right? And we actually will get again 2 root 3 because sine is positive in the second quadrant as well. And then this is approximately 3.5, right? What about 3 pi over 4? You get exactly again 2 root 2. And then what if you do 5 pi over 6? Well, then you get a 2. And what if you do finally pi? Sine of that is, so you get a 0, right? And what happens is these points are actually symmetric if you think about it. If you go 60 degrees or another 60 degrees, which is 2 pi over 3, right, the 120 total, you again end up with about a 2 root 3. And then what if you go 3 pi over 4, that's the 45 degrees reference angle here, you go again about what is it, 2.8-ish, right? And then what about the 5 pi over 6, right, the 150 degrees, you're about right here with a 2, so 1, 2, and you're right here about. And finally, you would go to 0 at pi, so this direction, but you're getting nothing, so you're going to be at the origin again. And look, what happens is, it kind of looks like a circle to me. Anyone think it's a circle looking thing? Why would it be a circle if it was a circle? And what radius? Looks like it's a radius 2, right? And that's 2. And so that's interesting, right? It's like a radius 2 circle centered at the point 0, 2. So is this circle with center what is that, 0, 2 and radius equal to 2? Is that the case? So let's see. By the way, that would be the equation x squared plus a y minus a 2 squared is equal to 4, right? Is that what we're getting? Well, we had, what did I give you? I gave you r equals 4 sine theta. Okay. R equals 4 sine theta. Now, what if I multiplied everything by r? For example, we can do that. So, and there are other ways, of course. You can just kind of say sine theta is actually a y over r, right? But let's go ahead and do r times everything times r. And what happens is we get r squared is equal to 4r sine theta. And what's nice about this is because r squared is actually, remember, x squared plus y squared. My 4 what? R sine theta is 4y. Remember that? And so what happens is if I simplify this further and complete the square, x squared plus y squared minus a 4y is equal to 0. Okay, x squared plus a what? Completing the square, this is y minus a 2 squared minus a 4 equals 0. And you do end up with x squared plus a y minus 2 squared is equal to 4. Sometimes the advantage of polar coordinates is that, first of all, the insight is a little different, but at the same time, you get the same shape. Also, look, this looks easier, the writing is easier here than all this mess of x and y squared stuff. And this actually has a lot of depth because, remember, you use a distance formula to prove the formula for the standard form of a circle as far as the rectangular equation for that goes. So let's do this. Let's now do one more example. All right, let's do one more example of polar graphing to kind of get a grasp on it. A little tougher, of course, this time. So let's get a big old rectangular axes going on here, and let's say this is maybe a 1, a 2, a 3. Okay, 1, 2, 3, and then up 1, up 2, up 3, down 1, down 2, down 3. Okay. Now we're going to graph. Look at this. Look what we're going to graph. We're going to graph r is equal to 3. Okay, ready? Cosine of. Let's make it fancy. Let's do something like 3 cosine 3 theta. Okay, we're tripling that angle. Okay, wow, what are we doing here, right? So this is going to be kind of tougher, right? So what happens is, let's look at, let's do kind of this r theta, right? But let me kind of give another continuation of that. So we're going to do a bunch of points first. Just kind of get a glimpse of what's going to happen. So look, this is theta. Let's put theta here and r there. Let's go ahead and start putting in numbers. I'm just going to do this rather quickly. So put a 0 in. Cosine of 0 is a 1, so you get a 3, right? Put a pi over. Let's actually do this. Let's do degrees. Put 10 degrees in. What do you get? 3/2 root 3, right? What about put a 15 degrees in? I'm getting a 3/2 root 2, okay? Because I'm getting at 45 degrees there. Let me try 20 degrees. And actually, if at 20 degrees, I get a 3/2. Okay? And then you continue going, and let's say 30 degrees. I get a 0. Interesting, right? Because cosine of 3 times 30 is going to be, let's actually do 20. What is that? We can do 30, yeah. 30 degrees, you get a 0. So you get 3. So you're getting smaller. Like you get, here you are at 0. At 10 degrees, you have 3 root. So 3/2 root 3, or the square root of, what is that? That's the square root of 27/4, which is the square root of about a 6 something. So not a square root of 9, but a square root of 6. So 2 something. Let's see. Anyway, it's going to be lower, so it's going to be smaller. So, but it's getting smaller, smaller, smaller. So eventually, you're going to, at 10 degrees, you're going to be right here somewhere, and you're going to be doing this. And then what happens is you're going to, you're going to get smaller a little bit as you're getting every angle smaller or bigger, or bigger angle gets, the bigger angle, the smaller the r, because the cosine is decreasing. Now look, you're going to 15 degrees, a little bit more, it's smaller. 20 degrees, it's now just 3/2. So 20 degrees is 3/2. You see how it's diminishing really quickly? And then what happens at more degrees, and if you get a 30 degrees, let's do 30, like right there, you go to 0. So you go back to basically like right here, kind of do that. You can decreasing as you get in bigger angles. Okay, we have some kind of weird shape like that. Let's continue further. Let's do 40 degrees, and you get again a, what is it? A 3/2, right? 1/2 of 3. And so, but now where's that? That's going to be right over here. Wait a second. So actually negative, right? Sorry, because this is 120 degrees. Cosine is a negative, so negative that. And so look, we're going at 30 degrees, or what is that? At 40 degrees right there. But we're going backwards, negative, right? So we're actually going to go this way. So this distance right here, let's see, this way. And so we're going to do this, and then you know what's going to happen? We're actually doing kind of the same thing we did there, but now we're going, let's go to this point here, okay? And not that one. We're going backwards, and we're getting backwards more and more and more until we get to what? What's 180 degrees? 60 degrees, and then that's going to be again a 0. So you're going to, at 60 degrees, or 60 right there about, you're going to go back to, actually 60 degrees, -1, so -3, right? Oops, that wasn't correct. Let's do -3. Okay, let me delete that 0 there, because of course a -1, cosine of 180 is a -1. So -3. So you're going to go at 60. You're going to go all the way maximum cosine can be, which is a -3. All right there. Okay, and that's going to be right there because you have a -3. So it's going to go like this, like this, like this, like this, and then what happens? Well, let's see. Then we're going to start decreasing. Think about 90 degrees. Then it's going to go to 0. Right, because 270 cosine of that is, so at 90 degrees when you're going this way, you're actually going to go not negative anymore, anything besides just 0, and you're coming back to just being a 0 like that. Okay, interesting what that is, because later we'll continue. Let's do 100 degrees, and you actually get again a -3/2. Okay, a little bit more, and you get a -3/2, and this is repeating. You see, if you think about the symmetry, but now it's positive. Well, this is positive by the way, right? Because at 300 degrees you get a positive 3/2. So you're going at 100 degrees, you're going out. And this is symmetric to what you had at this 120. It's going to be actually, what is it, right here, like that. So right there, it's like that spot. And so we have that, no, not that one, but this one right here. And so you're going out, 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 out more, because the cosine is going to get more and more and more as you're getting from, you know, from 270 when you triple that to 300 to, let's even do, what is it? How do I get again a 360? 120 degrees, right? To triple that, you get actually a 30 then. Triple, I mean 3 cosine of 300. 60 degrees is going to be, where is it? It's going to be a specifically a 3 now, right? 3 times 1, and so you're going to get a maximum cosine again at 120 degrees. That's right there about, and you're going to go out to the exact maximum of 3. Okay. So this is very, very difficult to conceptually grasp, especially initially. And then, of course, that's the maximum there, and guess what happens later? And this is kind of symmetric to this point. You see that one right there? So it should be a very similar point right there, okay? And then guess what? It's going to start going down because you're after 360 degrees. The cosine, you know, is going to continue to 450, similarly how we did here, because you're tripling the angle. And so if you go to, let's see, what's another time you get when you get 0 again? How about 150 degrees and you get 0? So 150 degrees right there, you're going to get 0. So you're going to come back to, you know, like that. You're going to come back to this 0. And guess what happens when you go from 150 on? Like, was it 454? Let's see, 160 degrees, 480. 480 actually, cosine of that is just like a cosine of 120. It's a -1/2. You get a negative. So you get negative, let me get rid of that, -3/2. So this is going backwards now, and so you're going to do this. You're going to, as you increase the angle from here to there, you're going backwards, so you're going to start doing this. And it's going to, of course, if you go to 180 degrees, you get again 0. Check that, okay? It's 540, cosine of that is 0. Or, hold on one second, cosine of 180 degrees, triple this cosine of 540, right? And that's a negative, well, that's a -3, of course. That's not a 0. When the total 3 times a -1. So 180 degrees, we get a -3. See, 180 degrees right here. But you're not going this way. You're going this way, right here. And so you're going to go backwards. And so you're going to actually get back to this point that we started with. And if you continue, you're going to get the same thing from the 180 to 360 degrees case. You see, we're going to go this, 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 and then we're going to continue, 180, 190, 200, 210, 220, and you eventually going this way, you're going to get the same actually following pattern. This one, 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 and it continues this way in this actual order. This is the direction of its motion. Right, kind of cool. And then that's what we did. And so that's that. This is called a rose with 3 petals. Wow, right? A beautiful graph. Rose with 3 petals. Actually, in mathematics, this is something called the rose with 3 petals. Okay. Wow. So hopefully that was interesting. And we're going to pause for now. But I want you to show, just give you a little glimpse of how to graph something maybe as challenging as, let's say we graph something as challenging as r equals to cosine of 3 theta, right? That's a tough one to graph. And you see how conceptually we had to think. As we increase the angle, you move in that direction, how much over the pole do you actually move? Okay, thanks for being here, and I hope you have a wonderful remainder of the day, evening, or wherever you are. I look forward to seeing you soon.